Hello guys, welcome back to another problem solution video. Today we've got another question here, and as always, let's first start off by reading the question. So, the sequence of positive integers with 2020 terms is called an FT sequence. If each term after the second is the sum of previous two terms. For example, if the first two terms of an FT sequence are 8 and 7, the sequence would begin as 8, 7, 15, 22, and then 37, and so on. For some positive integer m, there are exactly 2,415 FT sequences, where the first two terms are each less than 2m, and the number of odd value terms is more than twice the number of even value terms. So what is the value of m? Now we'll look at the parity of the first two integers in a list, and the property of an integer being either, let's say, even or odd, so like 1 and 2, whether or not they're even or odd is called parity. Now, if two integers have the same parity and they're added together, it will be even integer. So odd plus odd is even plus even is odd. However, adding two integers that have a different parity is going to be an odd integer. Now, this means that we can begin with a couple possibilities. So in total, for our two different terms that can start off with an FT sequence, there are 4 different possibilities for the parities of the first two terms of an FT sequence. So, for example, we have different options. Let's say we start off with odd and odd, or we start off with even and even. So I represent with e's or o's. After that, we have odd and even, or you can have even and odd. And after that, they'll sort of have a pattern to them. So for example, let's go to the first one. It'll be odd, odd, even, odd, odd, even, and so on. For the second one, it's going to be even, 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 even forever. And for the third and fourth one, it's going to be similar. So odd, odd, even, odd. And then for the last one, it's going to be even, odd, odd, even, odd, odd. Now we need the total number of odd numbers to be more than twice the number of even value ones. So already sequence 2 is not possible. We can't have a sequence with only even numbers. So that means that our only possible sequence are these three. Now, however, we'll eliminate sequence number 4 later on. But let's first look at sequence number 1. Now, as you can see here, we have a sequence beginning with odd, odd, even, odd, odd, even. So total, there's sort of a core of the pattern, which is 3 terms: odd, odd, even, and then repeats. Now, since we have 2020 terms in this sequence, we'll see that since 2019 is divisible by 3, it's going to be equal to 3 times 673. We can see that up until 2019, there's going to be exactly double the odd numbers compared to the even numbers. But now let's look at 2020, the 2020th term. Now, 2020th term has a remainder of 1 when divisible by 3, which means it's going to be the first term in our core, or 0. So this means that if we have this sort of pattern all the way to the 2020th term, we're going to have our odd value terms be more than twice the number of even value terms. And the same logic can be applied to number 3, or sequence number 3. In our pattern, it'll also be the same thing as the first. So sort of like a right line here, so you can see the core of the pattern. So just ignore the second one. As you can see here, it begins with odd, and then even, and then odd. And since the first term is going to be odd, it will also apply. So that means our third. So these two both work. However, our fourth sequence does not work here, and our pattern does not work. Why? Well, because if we apply the same logic for this one, we can see that the 2020th term is going to be even, which is not possible, because this means that our condition here, so that the number of odd value terms is more than twice the number of even value terms, doesn't work here, so we just can't have it. This means that these are going to be our only two possible patterns. Now let's look at what these first two terms could be. So, how many FT sequences begin with 2 odd value terms, in each of which is a positive integer less than 2m? So this means that there are 2m minus 1 integers that we can sort of compile. We can pick out one integer from this sort of list. So there's going to be 2m minus 1 positive integers that are less than 2m. Now, since m is going to be a positive integer, we know that 2m is going to be even. Since 2m is always going to be even, this means that 2m minus 1 is going to be odd. And since we start at 1, this means that from the list of integers from 1 to 2m minus 1, there should be a total of m integers. So there's going to be m number of integers that are going to be odd, and m minus 1 number of integers that are going to be even. And why is this? Well, because 1 is odd, and 2m minus 1 is also odd. So this means that in the both ends of the sequence are odd, and obviously there's going to be one more odd number compared to even numbers. So we have this, we just divide it by 2, and then we add 0.5. Now this means that the total number of possibilities that we have should be just m squared. Why? Well, for our first term, there's m possibilities for odd numbers, and for our second term, it's also going to be m different possibilities. So it's just going to be m times n, or m squared. So now let's look at the third sequence. Now the third sequence, as I said before, is going to be, the first two terms are going to be odd and then even. So obviously I just read out, so the number of possibilities for the number to be, so the number of different integers that are underneath 2m minus 1 that are odd is m, and vice versa for even, but it's going to be m minus 1. So this means, since we need an odd and even, it's going to be equal to m times n minus 1. Now this is going to be expanded into m squared plus m squared minus m, which is going to be equal to 2m squared minus m. And this should be equal to our exact number of 2,415 total FT sequences that we can have that match this condition. Now we need to solve for this, and we'll be able to see that we just plug into numbers there. Let's say that m is going to be equal to 30. So this is going to be our base number. If m is equal to 30, we can solve for this, and this is going to turn into 30 squared plus 30 times 29, which is just going to be equal to 1,770. And this is obviously not our number that we need. So after this, we can just keep on adding and see when it becomes this number, which is 2,415. So then you can plug in m equals 31, m equals 32, and finally you'll see that when m is equal to 33, we get 33 squared plus 33 times 32, or 2,145. This means that m is going to be equal to 33. However, oh sorry, I did this wrong. As you can see here, 33 also does not work here, as it's 2,145, and as we need 2,415. Sorry. So this means that we just need to keep on adding more, and then we can see that when m is going to equal to 35, this is going to be the perfect number that we need. So 35 squared plus 35 times 34 is going to be equal to 2,415 as required. So this means our answer should be D, 35. So yet again, I'll say this again, it's not equal to 33, I got this messed up. It's actually going to be equal to 35. So we start off with m, we just plug in m equals 30, and we see that it's too small. Then we plug in m equals 33, it's still too small, and we just keep on adding 1 into m and plugging it in, so we eventually get that m is going to be equal to 35, or 2,415. So this means that our answer should be 35, or D. Thank you guys for listening. If you have any other way to solve this problem, please comment down in the comments, and thank you guys for listening. Bye.